Yeah, hi everyone. Am I audible?
Yes.
Okay, great. So Ashish, can you please stop sharing your screen so that I can share mine?
Yeah, I'm just doing.
Perfect. Yeah, so great lecture. I think he covered most of the basics, like what gates are, how do we analyze a quantum circuit, and building upon the basics which he had just covered, I'll be introducing you to a demo of Qiskit, which is the IBM SDK offered by IBM. Uh, and free of cost. That's a major bonus over here. The complete SDK is available as cloud computing and it's free of cost to all of you. So you can all make an account over there and start doing all these calculations, building all the quantum circuits on the cloud itself without paying any penny and right from your home. Okay, so till the time I get the rights for sharing, I'll just give a brief intro of myself. Hi everyone, my name is Vardaan. I'm currently pursuing a master's in physics. I am a Qiskit advocate for the past few months, and I have been working in this research work of quantum computation for over an year now. I have worked as a quantum developer at Artificial Brain Technologies, and for the past few months, I've been associated with TCS Research and Development Cell as a quantum research intern. Okay, so I'll start sharing my screen now. I hope it's visible. Just give me a thumbs up whenever the screen is visible to all of you. Perfect. So yeah, before starting with what Qiskit is, I just wanted to give this resource to all of you. This is the Qiskit textbook. It's I think one of the best resources available out there for learning quantum computation, especially on the IBM Cloud Network. So you can just log on, browse as qiskit.org/learn, and this site will open. And this is a textbook which covers all the areas, all the domains regarding computation in quantum. So it starts with an introductory course. It covers all the prereqs. It even covers all the quantum states, qubits, entanglement. I mean, everything from quantum protocols to algorithms to even microwave pulses and even certain applications. Like we have certain applications for logistics over here. We covered quantum machine learning over here. So right from A to Z, everything is covered in this particular textbook, and it's one of the best resources out there to for you to study. I think everything that will be covered in this 3-day long course hosted by Qkrishi will be covered in this textbook in some format or the other. So it's a great resource for all of you. Just hop on and just study at your free time. Moving on to IBM Qiskit. So this is the dashboard. I'll just show you how to log in. Just give me a minute. So this is the interface for the IBM Quantum login, right? And this is what you get when you go to this particular website. So you just need to go to quantum-computing.ibm.com. This particular screen will open. Ideally, you would have to create an IBM ID account over here, or you could also sign in via Google, GitHub, or LinkedIn. If you've already created an account, just go to IBM ID over here and sign in. Right, so I'll just quickly sign in. Signing in. This is the particular dashboard which you'll be receiving. Okay, just give me a minute. I think double authentication is switched on for me. So, okay, no problems. So this is the dashboard which you will be viewing once you log into the IBM Quantum network, right? So I'll give a brief intro of what all the different aspects of this dashboard is, and then we'll come to some of the core concepts of demo in this particular session. So first part which you see is the most important one, which is the API token given over here. So this API token is a unique code which has been assigned to you as your login ID by IBM itself. And this particular API token is used for you whenever you are trying to solve or run a particular quantum circuit onto the cloud network provided by IBM. So whenever you run a circuit, whenever you do some computation via cloud, this particular API token is taken into account. Now, this particular API token is personal, it's very private to you, so I would not recommend sharing this with anyone. Although, if by chance this gets leaked, right? So just say I copy this and I paste it somewhere which should not have pasted. I can just refresh this over here, and a new API token will be generated right away by IBM. Okay, so this is just a safety feature which IBM has provided. Just in case your API token gets leaked, you can always regenerate it over here. Two other things which you might notice in this dashboard is the IBM Quantum Composer and the IBM Quantum Lab. And I'll just come to that in a short while. These are very important two shortcuts provided over here. I'll come to that later. The other thing on this dashboard are these notifications. So these notifications basically tell us that if there is any maintenance plan for the IBM servers, or maybe if any server is being retired, just like over here, or maybe if a new server is being added. So anything which IBM Quantum needs the users to know, everything will come over here in the recent notifications panel. Other than that, we have some special access programs over here. So I'll just go to this top left browser over here, and this toolbar appears. Again, we have some shortcuts for Composer and Lab over here. We have some compute resources. I'll come to that in just a minute. But right now I need to talk about these programs. So the IBM Quantum provides three types of access. One is the open access, which you all will be getting as soon as you create an account. Other than that, there are two more access special privileges. One is the researchers program and the other one is the educators program. And as the name suggests, these are specifically designed for researchers and educators respectively. So if in the audience, I'm not sure what the audience consists of at the moment, but if in the audience someone is planning to go for research in this particular field, I would recommend applying for this researchers program. So you would be granted certain special privileges, maybe some certain cloud access which runs your jobs faster, runs your quantum circuits faster, or maybe access to some privileged machines, privileged quantum machines, quantum hardwares, which is not open to the general public. In a similar way, educators program is designed for someone who wants to teach this particular Qiskit software to the students. So if in the audience there are some teachers or educators present, the educators program is one for you. It's very easy to apply, and usually in a week or a month's time, you are granted the access to these programs also. Talking about the program, once you get the special access over here to either the researcher or the educators program, you can verify that by going to this profile icon over here and just go to account settings. And in this particular account details, you will get a notification that you have been added to a special program. And just a fallback option over here, you can even check how many providers are available to you. So this particular account which I'm running right now is a general purpose open to public account. And the only provider available to me is the open account, IBM Q Open, right? It consists of 6 hardwares and 5 simulators. I'll just talk about them in a minute. If in case you are selected for those special privileged programs, right, either the researcher or the educators program, you would have access to a few more providers, which would either grant you access to different system and simulators. So maybe instead of 6 systems, you may have access to 10 systems or 20 systems, depending on what particular program you're selected for. Or you might have access to privileged runtime accessories. So if you're running a circuit, your circuit will be directly jump to the front of the queue. So you do not have to wait for the complete queue. Now, what do I mean by queue? I'll again come to a minute. I know I'm jumping a lot of stuff over here, but I'm trying to cover most of what is there in this quantum IBM Quantum dashboard, right? And that covers like the basic layout. Now let me start with the composer. So you can launch the composer by pressing right at the shortcut present over here, or you can go to this menu and again go to this composer. Similarly, for opening the IBM Quantum Lab, you can use the shortcut or from over here. Before that, a small divergence, I'll talk about the compute resources. So this is a list of all the quantum hardwares which are available to me, which I can use right now without paying a penny. It's all free, right? So your resources under this tab, all these hardwares are available for me to run my quantum circuits on, and all these simulators are also available to me to run my circuits free of cost, run my all my quantum computation programs right from my home. You don't need to pay a penny. I'm again repeating this because it's actually quite exciting. You are able to access these quantum hardware machines right from your home for free, and that's quite a big thing, right? But other than these few 5 qubit and 7 qubit resources, we have certain more resources which will be covered in this all systems. So these resources are not available to you as yet, okay, because you are in the general open program right now. But if you want access to these programs, you can either go by the pay as you go access, like you start using these machines right away, and the more you use, the more credits will be cut from your account. So either you can use that, or you can join the educators or researchers program, which will grant some of these machines for some time to you to do your research or do your teaching stuff. Okay. Similar to these hardware systems, we also have certain simulators available to us. Now, simulators are not the same as hardwares in just one major thing. These are not actual hardware machines. Okay, these are just artificially creating some certain noise and artificially simulating what happens inside a quantum hardware onto your system. So these are not exactly a quantum computer per se, but these replicate the functioning of a quantum computer. And finally, let me start with the composer. Okay, so I'll just head over here to IBM Quantum Composer. And this by far is the most interesting thing of IBM Quantum. Okay, it's so simple to use, it's so interactive to use, and it's like so basic and trivial in its knowledge that it actually has no use in research or in like once you get experience with quantum labs. I don't think anyone uses quantum computer, but it's a very good resource to at least start from the beginning. Okay. Before I start, I'll just open a new circuit over here, and I just want you to ask any questions that you have. Okay. So if there are any questions, you can shoot me. I cannot see the chat over here, so if you do have any questions, you'll have to unmute yourselves and ask me. Okay. So I'll just take a minute over here. If anyone has any questions, you can ask me right now. Okay, it seems no questions as of now.
Hi.
Perfect.
One question.
Yeah.
In upper right section, in the message Qiskit, is in a select option. What is the difference with QSM? If you click in Qiskit, in Qiskit, in option, in the upper option, upper right option.
Yeah.
Left. Down. No in a menu. No in a menu. In the language. Down. Other. Yeah. And select.
These options?
Yeah. What is different from OpenQSM?
Okay, I'll just come to that. Yeah, that's a good question. I'll come to that in a minute. I'm happy that you have already started exploring this particular dashboard. I'm coming to this in just a minute. Okay, just hold on for some time. Once there's generate a circuit over here, you'll better understand what this actually means. Okay. Any other doubts other than that? Okay, so let's start with over here. So I'll again give a brief intro as to what all is present over here. These icons which you see over here are actually the quantum gates, which you might have already studied in your previous lectures. So all these gates can be simply picked up from over here and applied to the quantum circuit over here. So these are actually quantum circuits. These are quantum bits represented by Q and classical bits or classical registers represented by C. So we have 4 quantum bits over here, 4 quantum registers, and similarly 4 classical registers present over here. For your simplicity, I'll just delete all these extra qubits and I'll just play around with 1 qubit right now so that it's easier for you to understand. Okay, I'm just deleting all these extra qubits and I'll even delete all the classical extra registers so that I have 1 classical register and 1 quantum register at the moment. So you see, I can just drag and drop any quantum gate and put it over here and a quantum circuit would be created. The best thing about this particular dashboard of quantum computer is you have a lot of interactive widgets present over here which are dynamic in nature. So as you're adding or as you're rearranging these gates, you see all these 3 components are getting changed in real time. The first one you see over here is the probability. So this actually gives you a probability of what the qubit is present in which state. So either the qubit is present in 0 state or it's present in the 1 state, you get a probability. So right now, there's a 50% probability of being present in state 0 and 50% of being present in state 1. And that is obvious, right? Because I've applied a Hadamard gate over here. Even if I remove this X gate from over here, we'll still have the same probability because X gate basically switches the state of the qubit from 0 to 1 and 1 to 0. But in case I do operate another gate over here, I'll have a different setup over here, and that is visible from the Q sphere over here. So Q sphere is actually representing which state the qubit resides in at the particular moment. Let me start with simple examples for you to understand better with the gates you already are aware of. Right now, at the present situation, without adding anything, there's no gate. This particular qubit number 0 is in the 0 state, which is observed in this probability. So 100% probability is that the qubit is in 0 state. Right? Makes sense? Initially, the qubit is initialized to a 0 state. Probability in 0 is 100%, and the same is represented in this Q sphere. So this purple dot over here is representing the state 0 of the qubit. The same thing is present in this code block over here, which is running Qiskit over here. So Qiskit is a programming language based on Python, and if you're not familiar with Qiskit, you can obviously go to OpenQASM, which is a simulator language. But the ideal thing is you need to learn Qiskit. Okay, so the first block is all these are actually importing certain libraries from the Qiskit so that the circuit can be run. The circuit actually starts from this Qreg over here. First, we define the quantum register. So we have 1 quantum register named Q. And that makes sense, right? We have 1 quantum register named Q. The counting starts from 0. So the first qubit will be named Q0. The second qubit will be named Q1. We'll come to that later. Similarly, I define a classical register next. Again, 1 in number and named by the letter C. So I have 1 classical register. Now, mind you, the counting of qubits start from 0, but the counting of classical registers start from 1. And this is something which you need to keep in mind for the rest of this lecture. Finally, I create a circuit named as quantum circuit based on certain quantum registers and certain classical registers. And since nothing is being done in the circuit, the rest of this code block is empty. In case you are not comfortable with Qiskit, just like someone mentioned, there's another option over here, which is OpenQASM 2.0. This is a simplified simulator language based only on simulations. You cannot program a quantum circuit using OpenQASM. You can just view whatever we are doing it here in a simpler language. So instead of all the inclusion of libraries, instead of all the jargon surrounding Qiskit. You just have one quantum register Qreg Q1, one classical register Creg C1. That's it. So it simplifies stuff for you to understand. But again, I'm repeating it again because using open chasm, you cannot make the quantum circuits from ground up level. So if anyone is familiar with programming, you need to know, right? You need to use Python or maybe C++ or any XYZ language to build circuits, to build computational programs. The same thing goes for quantum computing as well. You need to build programs. Everything cannot be done by just simple drag and drop things, right? This might work well for small, very small circuits, but as you go on to quantum algorithms and you learn more difficult circuits, or maybe you want to tackle more advanced problems, you will have to deal with programming where Qiskit will be your better friend. OpenChasm will not help you program stuff. So right now I'll deal with Qiskit only. If in case someone has trouble understanding what this particular program is doing, you can anytime go back to the OpenChasm option and understand what this actually means. It's just a simple way of representing, that's all. I hope I answered the question which was asked earlier.
Okay,
Right?
okay. Thanks.
Perfect. Moving on, I'll start building the circuit. So let's start with the most simple quantum gate, that is the X gate. Now, the X gate in IBM Quantum is represented by this plus sign. Okay, it's not a simple X. This might be confusing initially, but eventually you get the hang of it. So this plus sign represents an X gate, and I apply this X gate onto the only qubit present over here. First thing you observe, you see after the quantum registers, another line has been added over here. The first line of your quantum circuit, which says circuit.x and a quantum register Q0. This means that onto the quantum circuit, X gate is being applied. And where is this X gate being applied? Onto the quantum register Q0. So we have quantum register Q0 and an X gate being applied over here. Two other observations that you make are these interactive widgets. Now this is really, really amazing, right? This is all happening in real time. It's so dynamic. As soon as I move the gate into the quantum circuit, the probability shifted from 0 to 1. And now I have 100% probability of the qubit existing in state 1. Why? Because I have applied an X gate, and as you all know, X gate shifts the quantum qubit from state 0 to 1 and 1 to 0. So initially it was in 0 state, now it is in 1 state with 100% probability because it's a simulation. There's no noise over here. And the same thing is observed in this Q sphere. So if you observe the state of this particular qubit, it has a phase angle 0, it has state 1 and probability 1. Okay, so this qubit has shifted from its original position, which was at the top of the Q sphere, and it has gone 180 degrees, pi degrees, right to the bottom using state 1. I hope the function of X gate is clear to all of you. Just for fun, I'll add another X gate to the same qubit, and I guess you all know what would the answer be. So 0 say 1, and then apply another X gate to 1, so the qubit again shifts back to its original position. First observation, another addition in the code line. So now we have another X gate being applied to the same qubit. Two more observations in the visual aspect. The probability has again shifted to the 0 probability. The state has again shifted back to the initial state of 0. And although this makes sense in a trivial manner that X gate shifts from 0 to 1, so 1 to 0 is also possible, this also underlines a hidden fact of the Hermitian property of these quantum gates, that they are reversible. So if whenever you apply two same quantum gates in succession, their operation gets cancelled out and you obtain the initial state. This is a very important property which you might want to keep in mind. So I'll just delete both these gates over here, and instead I'll try using a different gate. Let's say a Hadamard gate. And now a funny thing is about to happen, because the operation of a Hadamard gate is a very peculiar one, right? It shifts the state of a qubit into two halves. It is equal to 1 by root 2 0 plus 1, if you remember correctly what Hadamard does to a 0 qubit. First observation, in the code block you can see this particular line. Instead of x being applied over here, we have h being applied over here, which is a notation for the Hadamard gate, again being applied on the Q0 quantum register. Two more visual observations. In the probability section, you can see that half the qubit is now present in 0 state with a probability 50%. Another half is present in state 1 with 50%. So this is something which is not possible classically. You cannot have a classical bit existing in two states at the same time. But in quantum computation, this is possible thanks to Hadamard gate. So the qubit is currently existing in two states with an equal probability, and this is amazing, right? Right. So this is so dynamical. This is so like a real-time visualization that you can actually observe how quantum computation works, and that's why IBM Quantum Computer is an amazing tool for beginners. In the Q sphere also, you can observe that you can have two states. One state is the 0 state with a probability of 0.5. The other state is one state with a probability of, again, 0.5, right? So these are some great visualization tools to help you get the hang of how quantum computation works. The next step would be for me to try creating, let's say, a Bell state. So I'll add certain qubits over here. I'll add one more qubit. So now I have two quantum registers, and I'll add another classical register as well. So I have two classical registers represented by C2 and two quantum registers represented by Q0 and Q1. How do I actually know that this is working and that I have successfully implemented? Just check in this code block over here. Now you can see that two quantum registers are being applied and two classical registers are being applied, and hence I verify my statement. Another thing which you might notice, as soon as I increase the number of quantum registers, the computational basis set in this probability histogram also changed. I'll just go back one step to help you realize what is being changed over here. Initially, I had the computational basis set as 0 and 1. 0, 0, 0, 1, just two states. If I add another quantum register and I add another classical register, the computational basis states have now increased to 4 in number. We have 0, 0, 0, 1, 1, 0, and 1, 1. Now, obviously, initially the circuit is initialized to state 0, and hence we have 100% probability over here. But if I start operating these using quantum gates over here, I'll see the difference in the probability. So now I have applied a Hadamard gate to the first qubit, and instantaneously I see a difference in the probability acting over here. What's the difference observed? The first qubit is no longer in the 0, 0 state. It has been divided into two parts. Half the qubit is present in 0, 0 state, and half the qubit is present in 0, 1 state. Right? The same thing is observed over here in the Q sphere as well. So you have half the qubit in 0, 0 state, half the qubit in 0, 1 state. And another thing which you might observe over here is the fact that we have no qubits in either 1, 0 or 1, 1 states. And that is why the rest of this Q sphere is empty and the rest of these probabilities are 0. Okay? I'll take a short break over here. If anyone has any doubts regarding this, just shoot your questions right now. If not, I'll continue creating a Bell state and we'll talk more about this in a minute. Okay? So if you have any questions, now is the time to ask.
I make changes in the Python code directly, will that be reflected on the graphics dashboard also?
That's a good question, actually. No, as long as you are restricted to this quantum composer, the code which you can not actually type the code here. Actually, you can type the code here, but it will not be like visualized in this quantum circuit, although it will be visualized in the probabilities and the Q sphere. So this code is editable, but I would actually suggest you to open this particular code in Quantum Lab. I'll just come to that in a minute. This code is much better edited in the Quantum Lab. Over there, you can actually do all the programming stuff. Quantum Composer is mainly focused for the drag and drop option. Okay, so it's not a vice versa thing. The drag and drop is translated into the code, but the code is not translated into the drag and drop option. Okay. So I'll continue with creating a Bell state for now. We have added a Hadamard gate on the first qubit. The second step to creating a Bell state is to add a C0 gate. Now this is one of the most famous like codes of all time, right? So you can get this example anywhere. I think Subhashi has also talked about creating Bell states in the later part of his lecture. And this is a Bell state creation, right? We add a Hadamard gate to the first qubit. We add a C0 gate to both the qubits, where the first qubit is acting as a control qubit, the second one is the target qubit, and the resultant is 50% probability in 0, 0 and 1, 1 states. In the Q sphere also the same is represented. We have 0, 0 and 1, 1 states with equal probabilities, and this is the maximal entangled state you can achieve with 2 qubits, also known as the Bell state. Right? If you want to actually have fun moving around with Bell states, you can just keep adding these X gates to the initial part of this Bell circuit, right? So if I add a quantum X gate to the first qubit, these states will change and you will have a different quantum entanglement. Similarly, if I add this X gate to the other qubit, you have a different quantum entanglement being here, present over here, and a different Bell state being achieved over here. If I add X gate to both the qubits, again, we'll have a different basis set obtained over here for both the qubits and a different entanglement obtained. Right? So you can play around with these qubits. And the best thing about Quantum Composer is you don't actually need to know the math behind it. I know Subhash is going to hate me for telling you this, but all the assignment questions could also be solved using the Quantum Composer itself, right? This is a cheat sheet kind of a thing. If you have to solve certain, let's say a combination of qubit gates, you can just add them using drag and drop and read the results from over here. Okay, everything is presented over here. And this is a great tool for like visualizing stuff, playing around with the qubits. You can add as many gates as you want, and you can see the results. It's as simple as that. In case you get into a certain kind of a difficulty and you don't know how to proceed, I'll again go back to this particular menu, and you can see all the documentation present over here as well. So you can just go to this drop-down menu, and we have these composer docs, where everything from A to Z for this IBM Quantum Composer experience has been written down over here, so you can get the help from there. Or you can go back to the resource which I shared for Qiskit textbook. You can have a look over there as well. And now I know that the lecture is about to end, so I'll quickly describe the Quantum Lab experience as well. I know that the time is like very small right now. I'll do it as quickly as possible. Okay, so let the Quantum Lab load. And Quantum Lab is the main, I should say, crux of the IBM quantum experience. Because once you get the hang of writing quantum circuits, this is where you will be doing everything. Okay, even if you're maybe doing some research in the industrial area or maybe academic work, anything related to quantum circuits, the IBM Quantum Lab is the one to use. IBM Quantum Composer is only for beginners to get the hang of quantum computing. So this is the dashboard which you obtain for the IBM Quantum Lab. And we have different file options present over here in which you can code this. So we have a Python kernels, we have Jupyter Labs present over here. For simplicity, I'll be using the Python kernel based on Jupyter Labs, which is hosted on the IBM SDK itself. Okay, this is a little bit simpler because the first cell of this Jupyter notebook automatically imports all the necessary libraries, all the necessary Qiskit tools required to build your circuit, right? Other than that, it also loads your IBM account. If you remember, right at the beginning of this lecture, I mentioned something about an API key, right? And I talked about providers. So this particular statement automatically fetches your API key from your account, and it automatically loads the open provider, which is by default used over here. In case you want to use another API key, so suppose you are working in an industry and you want your client's API key to be running this particular program. So over here, you can change that API key. Also, if you are having special privileged access to either the researchers program or the educators program, you can again use this particular statement, modify it, and use a different provider for that purpose, right? Over here, you can start coding all your stuff. I won't go into the codes right now. I think we are like reaching the end of this session. But I think one of the code files has already been shared on the WhatsApp group. It was a Jupyter Lab, so I know it's the same thing which I'm talking about over here. But right from the next cell, you can start coding all what we have done in the previous quantum experience for the composer thing in the lab part. Okay, so whatever you code over here will be actually running on the backends over cloud at quantum hardwares. Right, so I just wanted to give you a brief demo of what the quantum lab actually looks like. If you actually want to see a circuit, I can just open one of my previous circuits. Let's say I open this particular circuit, and this is what the circuit actually looks like. Right, the first cell is again loading all the important libraries and using your API key. And right from the very next step, you can start coding everything. So in this particular circuit, I know this sounds a bit weird to you. You have not actually studied the quantum algorithms yet. But this is actually the Bernstein-Vazirani algorithm, in which you first state the number of qubits and the number of circuits. So you see a quantum circuit is being defined here. Some steps you might be familiar with, like QC.X is basically quantum circuit dot X gate is being applied over here. On which qubit number n, and n is equal to 4 over here, right? So we have certain snippets, and again, all the results could also be viewed over here in the lab itself. And with this, I guess I come to the end of this session. I'll again go back to the dashboard, and now it's time for you to ask any questions that you might have. Okay, regarding the lab or the quantum computer, any questions are welcome at this point.
More than I have.
Yeah.
I have to. One is basically Subhash spoke about quantum parallelism and superposition. Is there a way to simulate that on this dashboard and kind of get an intuitive understanding? Do you have any code or any demos?
Absolutely. Just give me a minute. I'll just again open Quantum Composer because it's a bit easier for you to understand visualizing stuff. As soon as I apply a Hadamard gate, we are actually talking about quantum parallelism taking place. Quantum parallelism, I think, is just a fancy word of saying that the qubit exists in two states parallelly, and we can compute certain operations on it simultaneously. So as soon as I apply this Hadamard gate, we have the state existing in two states at the same point of time. So any other operation I apply after it, so let's say I applied a C0 gate, is actually being applied to both the qubits at the same time. This is a Bell state. Now these two states have been entangled. Again, if I add another gate, this gate is being applied, operations are being applied to both the qubits at the same time. And this is an example of quantum parallelism, because this is not possible in classical computing, right? You can either apply a certain operation onto one bit, or let's say another bit. Can I apply the same operation on two different bits at the same time? But this is possible in quantum, where any operation is actually being acted upon on both the states of the qubit, because these are quantumly entangled, and quantum parallelism comes into picture over here. I hope this makes sense.
Got it.
Hi.
One.
Okay.
Go ahead. I'll ask
Uh,
it.
Could you also give us a brief about Qiskit Advocate or some challenges? How difficult are they gonna be? And can we simulate them in the composer, or else do we have to work them on the lab? About the Qiskit Advocate challenges and those, like any brief on that thing?
Right.
Yeah.
So if you're asking about what kind of challenges there are certain, I would say, tough challenges, especially if you're beginner in this field. I would say you have to like study hard for at least a month or so before starting to actually solve those challenges. But once you get the hang of it, you would be able to solve this. I started my journey about an year ago, and now I'm actually quite comfortable with it. So it takes time. Okay, you need to do some hard work into it, but it's achievable. Okay, I won't say it's not achievable. It's very difficult. It is achievable. You will be able to solve challenges. Even the Qiskit Advocate program is quite easy to get into, as long as you are consistent on IBM Quantum. And the second question, if everything is achievable on Quantum Composer, my frank answer would be no. Okay, you can use the Quantum Composer only up to a limit. After a certain quantum depth or quantum circuits, this starts getting irritating to me, frankly speaking, because each time you want to add a gate, you need to drag and drop over here. You need to add certain more number of qubits, more quantum registers. Programming is a little bit more easier, right? You just add one code bit over here, you just change the number over here for the number of registers or the quantum qubits, and everything falls into place accordingly. So if you are going further, if you are further studying the subject, I would advise you to learn Qiskit as a programming language and solve all your problems using Quantum Lab. Quantum Composer is, again, just a tool for beginners to start visualizing what is actually happening in this particular domain.
Yes. Yes. Thank you. On that part.
Any other questions?
Vardaan, if you see, I think Google was the first one to kind of announce supremacy, quantum supremacy, and immediately, like a lot of other companies also claimed that they had that, right? So why IBM only? Why Qiskit? And are there any other similar tools given by different vendors?
Yeah, so that's again a good question. It depends upon what you're familiar with, right? Even in the classical computing, you have different programming languages available. But the thing about classical computing is the systems are available to you to use on. Everyone has a laptop these days. Everyone can run C++, Python, or any XYZ programming language according to their needs on their personal systems. But quantum's hardwares are not that easily available yet. There are a handful of them in the whole world right now, and only a few companies are actually providing them for free. Yes, Google also has its own quantum programming language known as CIRQ, CIRQ. There are many more quantum languages as well, such as Xanadu, which just had been talked about, has its own penny lane language. But the access to the computers, their hardware is a bit limited. IBM, on the other hand, offers a whole lot of computers, whole lot of hardwares for completely free to you. So that's why I think it's an advantage to use Qiskit. But it's again up to you. Once you start getting the hang of using quantum computation for solving problems, you can actually shift your focus to other languages as well, use paid versions as well to solve your problems, and that's absolutely up to you. Okay, there's no restriction over there.
Vardaan, you can absolutely continue. The class is still 4.
Oh, that's great. So I've got the confirmation from Shri. I can actually continue fiddling around with these gates a little more. So I'll continue with this question session for another 5 minutes. If you have any doubts, you can keep them coming to me. If not, I'll continue with this session and talk more about how these gates are actually working over here, take a few more examples, and help you visualize this stuff in more detail. Okay. So if there are any more questions, just ask me right now.
Hi, one question.
Yep.
How can a Qiskit algorithm be invoked from a classic Python program? Any manual or tutorial?
Yeah, so I'll again refer you back to this Qiskit textbook. You might feel that I am a bit biased towards this textbook, but yeah, I'm actually a lot more biased towards this. So this textbook covers everything, right? From the introductory course to the prereqs, all the algorithms, all the stuff you need to know about Qiskit is present in this textbook. It's a great resource. Another resource which you might, if you want like old school and you want a hard copy of it, Nelson and Chuang is a good book for quantum information technology. So if you want to understand the theory behind Qiskit and how these quantum circuits are actually working, Nelson and Chuang is a good book. I link them in the WhatsApp group later on. Another good book is Dancing with Qubits. Now that is a more programming related book. So if you don't want to go into the theory and you only want to know how the circuits are being created or how do I program a particular quantum algorithm, Dancing with Qubits is a good book.
Oh, thanks. Thanks.
Great. Any other doubts?
Hello.
Then
Yeah.
one theoretical question, not related to the tool.
Yes.
There were multiple architectures described, right? One is superconductor, and the other one is photon based. And so, should we be agnostic about this underlying architecture, or certain problems are well? I know there was some introductory session saying that some type of architecture are better fitted for speed, some type of architecture is better fitted by accuracy. But generally, when you're using this tool, I don't think we get an option of like which architecture to choose. So how do we decide like which problem has to be here and which first of all, how to identify which architecture this tool is using?
Okay, talking about hardwares, now this is actually a question for the hardware companies and not related to you at all. So when you're programming, whichever language you choose to program your circuits is like by default programmed for a certain hardware. So if you are using Qiskit, you don't actually get an option to choose the hardwares now. You are restricted only to the IBM hardware. And IBM hardware is based on superconducting qubits. Okay, so that's a limitation over here. And that goes for any language whatsoever. If you are using Google's Circ language, you are restricted only to the Google's hardware. And Google might be using some kind of a hardware. If you are using D-Wave's language, you will be only restricted to the D-Wave hardware, which is a quantum annealing in nature, right? So the language you choose decides what type of hardware you will be running your circuits on, and that is for not you to decide, in at least in the beginning stage. Once you are comfortable with many languages and you are actually trying to solve a certain problem or doing your research, over then you actually have to decide, okay, I need to solve a logistics problem, and that logistics problem is on a large scale. So which hardware is more related to that particular problem? So you have certain options based on those hardware system. You choose the language, and then you decide which language I need to use my or build my circuits. Similar goes for other applications as well. So if you say that, okay, I need to build a program based on quantum machine learning, right? It's a very fascinating field, gaining a hype for the past few months. So you again see that there are, let's say, 5 hardwares available to you, and you see that which hardware gives me the least amount of error for quantum machine learning, or which hardware is best suited for the type or the scale of problem I'm trying to solve. Based on your problem, you choose the hardware, and based on your hardware, you choose the language in which you're going to code. Okay, I hope that answers your question.
Sure, definitely. Thank you.
Great. Okay, so if there are no more questions, I'd like to continue with my lecture. Again, I'm again coming back to Quantum Composer because, as I said, it's a little bit more easier to visualize. Right now, everything which I was doing in this quantum circuit was being visualized on these interactive widgets in real time. But a common query which you might have at this moment is this actually being run on a quantum computer? If yes, why is it so fast? After all, I'm working on a cloud computing network, right? So it should take a tiny bit of amount for the circuits to build and the answers to be visualized over here, the results to be visualized over here. And if you're getting that query right now, it's absolutely correct. These are pure simulations, okay? These are not quantum hardwares being run at the moment. So whatever you do right now, these are not actually the results. These are some simulations which help you understand. If you need to actually measure these states, if you actually need to run this quantum circuit on a quantum hardware, there are certain steps involved in that. So I'll cover all these steps right now. Let's say I have created a bell state over here, 0, 0, 1, 1 having 50% probability each. Now I need to run this particular circuit on a quantum hardware. First step is to measure this circuit. For measuring this circuit, I use this control thing over here, represented by a speedometer kind of a meter thing followed by a Z symbol. So this actually represents the measurement of a qubit. First, I measure it upon the Q0 qubit. Then I measure it upon the Q1 qubit. After both the measurements have been taken place, you see again, the probabilities are restricted to 0, 0 and 0, 1. But now they have been measured. And once they have been measured, I can actually use this option over here to set up and run. Only after I use this option, this circuit will be actually run on a quantum device over the cloud at IBM. Okay, right now it was not being run. It's just a false a hope kind of thing. These are all just simulations. You can only run this after the measurements have been taken place. And now I press setup and run. And once I do that, I get a lot of options over here. Step 1, choose a system or a simulator. I get all the options available to me for free right now. So I have different hardwares available to me. I have IBM Nairobi, which has a 7 qubits limit, and right now 79 jobs are pending. So just like my circuit, 79 more people are actually using this and they're queued over here. So there's no use actually queuing my code over here because it will take a long time. Let me go to the next one. I have IBM Oslo. Again, a 7 qubit limit and a lot of online users whose jobs are pending. Again, it won't be solved right now. I keep browsing down and I see that all the hardwares are actually having a long queue. And that is obvious, right? You provide something for free and people will just run anything on them. And the same happens for IBM quantum systems as well. If you have an open account, a free account, you will be expected to be in a queue for a long time. So even if I use this hardware right now, let's say I choose IBM Bellum, only 13 queues right now. I choose the shots, I name my job, let's say I type Qkrishi test circuit, and I say run on IBM Q Bellum. Now see, this would start running, it would queue my job and my job will be seen over here. So this particular tab over here lets me see all the jobs which I have run right now. So you can see pending, this particular Qkrishi test job has been created and it's pending. It's in the queue. If I press this particular thing, I'll get more details as to what is the waiting time, how much time I can expect before the circuit is being run. Expected to run in 3 minutes. Okay, that's actually quite, I would say, good right now. You don't actually get this sort of runtime for free systems. So after 3 minutes, we'll come back to this and see the results over here. But right for now, this is what measurement actually feels like. Similarly, I can again go back to setup and run, and instead of using a hardware system, I can use a simulator system. So I can go back down over here. I use the state vector simulator. For a state vector simulator, since it's a simulator, the run times are very small. Okay. So I can again go back over here, see my results in this jobs tab, and you can see it's already been completed as well. So this Qkrishi test circuit has been simulated over a state vector simulator. You can see the results which were as expected, right? You were expected to get half the state in 1, 1, half the state in 0, 0, and that is what is being present over here. Now, mind you, simulators are again at the end simulator, right? These are not actual hardwares being run. Actual hardwares will take certain time, and we can come back to that later on if that does run in this particular time. If you do have access to certain these privileged programs, the runtime would be reduced by a lot, and you can have access to certain different machines and a much lesser runtime. So that is something you can look forward to at your own free time. And now I'll just do away with this composer part. I think I've talked about it enough. Instead, I'll move on to the quantum lab experience. Okay, so let me just take a shortcut over here, and I'll try to code the same thing on a quantum lab. So I can just press this button over here, open in quantum lab, and it will open the same circuit on a quantum lab experience. Okay, this is where the major coding happens, all the programming happens. Okay. So this is the particular circuit which was being run over here. If I run this circuit, this is the circuit, right? This circuit has been visualized, and this circuit will follow whatever I do over here. So let's say I want to change this particular circuit. Instead of the drag and drop right now, I can actually code this. So let's say I now need a 3-qubit quantum resistor. I need a 3 classical registers. I want a Hadamard gate on the first one. I want a CX gate, a control NOT gate, 0 to 1 on the second one. And I want another controlled NOT gate, but this time from the first qubit, the control qubit should be the 0 qubit. The target qubit should be the third qubit. Okay, instead of the second one, it should be the third one. So for that, I'll just change the target qubit as 2 over here. Okay, I hope this particular code line makes sense. So what will be expected now? This is actually the creation of a GHD state. GHD stands for Greenberg Horn-Zeilinger state, which is the quantum entanglement of 3 qubits. So I just run this code block again, and this is the new qubit which has been formed, right? Hadamard gate on the first qubit, a C0 gate from 0 to 1, another C0 gate, but this time from 0 to qubit 3, which is Q2. This particular C0 gate is a special kind of C0 gate because it is not being applied onto adjacent qubits. And this is something which you need to keep in mind when you are accessing special hardware machines as to which qubits are adjacent to each other, which are not. That is some advanced stuff. Okay, you don't need to worry about that right now. Right now, you just need to see that this this operation is being controlled by the 0 qubit, but targeted onto Q2. So that means depending upon what the result of the 0 qubit is, my second qubit will be affected. I hope that is clear to everyone, right? In a similar manner, I can do anything over here. I can change the circuit as to my liking, and after the complete circuit is done, I need to measure the circuit. So there's one mistake over here. I have 3 qubits, I have 3 quantum classical registers, but all 3 qubits are not being measured. So I need to add another measurement command over here. So I'll just add that over here. Right, so we have Qreg. Q2, which is the third qubit in number, and it is measured upon the classical register Creg C2. Please keep in mind the numbering. The numbering of the classical registers and the quantum registers is a little bit different, and you need to keep that in mind. I'll run the circuit again, and the same operations could be applied over here. So you see this additional block of measurement has been added onto the third qubit as well. Similar to Hadamard, similar to control NOT gates, we can have any other type of gate as well, right? So just for fun purposes, this circuit does not mean anything right now. I'll add different types of gates over here. So let's say I want to add a Z gate over here to the first qubit. I write the same syntax circuit, and now I have the Z gate being operated over here. Z gate, Q register, Q, and which qubit I'm applying on? This is first one, which is Q0. And I again run the circuit. After the Hadamard gate, a Z gate has been applied onto the first qubit. Got it? Similar to a Z qubit, you can have any other type of gate as well. You can have Toffoli gates, you can have swap gates, any other gates you can have. If you don't know, or if you maybe forget what is the syntax, I'll again advise you go back to this quantum Qiskit textbook, or you refer to the documentation present over here. So just like I had composer docs, I also have lab docs over here, which goes into details as to how to code or how to create circuits. So if you, let's say I want to create another circuit, instead of a Z gate, I want to apply, let's say, a Y gate. Okay, a Y gate onto randomly, let's say, the third qubit. So that would be Q2 in number. Okay, syntax would be something like this. I run it again, and here you go. I've added a Y gate to this third qubit, which is Q2. And the same thing can be applied for any type of gate over here. These are all different types of gates which are available over here. You can add any gate. There are certain special gates also available in which you actually define the rotation. So those are rotation gates. I'll talk. I don't think that's it's good to talk about them right now because it's a little bit advanced. I'll not confuse you all right now. I'll keep you only restricted to the basics, so at least you understand what is being done over here. Similar to controlled X gates, we also have controlled Y gates or controlled Z gates. Again, run on a similar fashion. So as you all can guess right now, I can use the same syntax. Instead of, let's say, control X, I now want a controlled Z gate over here. So I say CZ, the syntax for controlled Z gate. Operated on the quantum register, which is acting as the control qubit over here, as Q, let's say 1. I'm mixing stuff over here just for fun. Followed by the target qubit, which is let's say control was 1, target was 2. So now essentially I should have a CZ gate, a controlled Z gate between 1 and 2. So let's just run and see if that happens. That happens, and this is what a controlled Z gate looks like. And important thing over here, controlled Z gate is the same as the swap gate. So a swap, oh sorry, I'm so sorry, a swap gate is a little bit different, but it has a similar symbol over here, so you cannot confuse that. I'm so sorry for making that comment. These are different gates, but yeah, controlled Z gate is something which is shown like this. Similarly, you can have controlled Y gates also. You can have simple XYZ gates. You can have controlled XYZ gates. You can have swap gates. You can have identity gates, Toffoli gates, and many more gates, right? You can have rotation gates as well. I hope this makes sense. I'll just pause again for a minute because I've talked a lot in a short span. So if anyone has any doubts, you can just ask your doubts right now.
So,
yeah.
Just to confirm, the control one, the control one targets the. Sir, I'm able to hear my voice. Like, is it on speaker or something?
Yeah, you are audible to me.
Not clear. Yeah, not clear. Okay, sir. I was asking that there's a control and there's one target, right? So the control one has an effect on target, or does the target also has some effect on the control when you do the measurements, right? Like when there are two involved.
Right.
Okay.
So as the name suggests, okay, control qubit is the one which is controlling everything. Target is the one on which the action happens. So okay, I'll just remove all the unnecessary stuff from over here, and I'll just talk about the control X gate. Let me just run this again. This is the control X gate, right? So the small dot represents the control. Q0 will be controlling the action. So if control qubit is 0, the Q2 will has its state reverse, or X gate will act upon it. If it is 1, nothing will happen. So the control is over here, the target is over here, so the action happens over here. The gate is being applied to the Q2 over here, controlled by Q0. Okay, I hope I'm making myself clear. Q0 controls it. The gate is applied only to the target operator. Okay?
Okay, sir.
Any other doubts? Yeah, so I guess this is the end of this particular demo lecture of quantum experience. Okay, so I'll stop sharing my screen, but if anyone has any doubts, you're welcome to ask me right now.
I have a question.
Yeah, sure.
So when, say, for example, we are doing some map reduce kind of work, like we are taking a whole lot of data and doing some computation and getting the output, right? So there we are dealing with at a very macro level. We are not dealing at a machine level coding or bit level coding, right? Though it's efficient, some engineers would do that level, but usually we stick at a very, like you have Python code, you write, okay, this is the data in some data structure, you apply some function and you get the output. Here I see like most of your demo, like what we have been taught till now at least is at a very bit level, right? Are there programming languages to do that? Like, okay, I want to do, map reduce. I want to apply some kind of sorting algorithm.
Yeah, so all those things could also be done using Python and Qiskit, but I'm not sure if you're asking if I could use a certain kind of language to actually change the hardware or work directly on the hardware. If that is what you're asking about, yes, there is a provision for that as well. It is known as Qiskit Pulse. Okay, That's a separate field altogether. It deals with more of the hardware, how the microwave pulses are acted upon the qubits, like what is actually happening, what's the physics behind that. So that is known as Qiskit pulse. You can check that out in your free time. But if you are concerned about running the programs up to whatever scale you want, Qiskit will help you do that. Okay, maybe a few qubits, a handful of qubits, which I've just run, and even if you have maybe 100 qubits, if the hardware allows, the language supports it. Okay.
Right, and we can also write a domain specific languages, right? On say in a Python, you have say Python version of bioinformatics or Python version of building a protein, right? That's a domain specific language which will map keywords which could use the, so it can be written, right?
Yeah, since Qiskit is actually Python based only, so everything which you already know from Python is applicable over here. You can install any other library packages or any stuff which you want to deal other than Qiskit and incorporate it with Qiskit, whichever suits you the best, right? So if you want to delve in machine learning or maybe logistic operations, you have certain libraries which are focused specifically for that. Or maybe if you want to do scientific work, we have libraries specific for those fields. So you can include those libraries using Python and incorporate them with Qiskit. There's no issue over there.
Got it.
Yeah, so if there are any other questions, I'm happy to answer them right now. If not, you can just hit me up over LinkedIn. I'm active over there, so you can chat with me over there as well.
I hope you have all had a basic idea about Qiskit, and thanks for Vardaan for making a very great presentation for Qiskit, starting with the basics and till taking to the quantum composers and quantum labs. It was a great session, and also thanks to Subhashis. I think he have already left. So
I have one last question.
Sure.
Like, based on my understanding, like we'll be able to implement or simulate multiple circuits, right, on this composer or on QLab. Can we use the similar things to kind of optimize our integrated circuits structure or something like for the chips? Like, do you understand the question?
Are you talking about a specific application related to chips or maybe circuit designing? Is that what you're asking?
Circuit designing, yeah.
Right. So optimization is supported by Qiskit. So if you want to maybe use a certain application for like designing a quantum circuit for solving a certain application, yeah, you're free to do that. If you are asking me about what or maybe how I can design the circuit for a quantum hardware.
No, I'm talking about a normal computer or normal, microcontroller or some kind of board. And for that also we'll be designing the circuits, right?
Right.
Can we use this architecture, and is it possible to, optimize that hardware?
Theoretically, it's possible, but physically, I don't know how feasible it would be, because the quantum hardwares do not use the same architecture as supported by the classical hardware. Okay, there's a big difference. If it would have been that easy, quantum computers would be popping up everywhere right now, right? But the quantum machines have a very, very peculiar kind of architecture in place, which is very hard to physically maneuver. So I'm not sure if it's physically possible, but theoretically, yes, the same concepts apply over there as well.
Okay. Yeah, that's it. Thank you.
Thanks a lot for the session and question. There were so many questions, and I hope everybody have a great idea now. And very important thing, please you all go back to the Qiskit session we had in the morning and evening. Try to do it yourself, try to build some circuits, and try to access the quantum computers and see what are the results you are getting. So all the code snippets are available online. If not, Vardaan is already available in WhatsApp. You can ask him; he'll be able to provide it. So you should be able to, should be very familiar at least with the fundamentals, how to add gates, how to make a circuit, and how to run. There's few different ways you can run a quantum circuit. So be familiar with at least one or two of them, and then only you'll be able to better understand the tomorrow session, because we will be going on to quantum algorithms like Dush-Josa and maybe teleportation and Dush-Josa. So tomorrow we'll be having a great session on bit advanced algorithms, and after that a project coming up. So it'll be having a great lot of coding tomorrow. So thanks for joining. Thanks a lot, Vardaan and Subhashis. And let us end the session and see you tomorrow. Bye-bye.
Thank you.
Thanks a lot,
Thank you.
everyone.
Thank you. Bye.
Thank you. Bye.